Today we're going to look at vectors, a little bit different concept. I'm going to go through it pretty quickly. So if you're not sure about some things, you might want to stop this video. There's an awful lot of concepts, definitions, and things we need to get through. And I do not feel comfortable just skipping over them and you picking them up later as we talk about them. So there's going to be quite a few clips here that just fill the board with words and definitions, and we'll move through them pretty quick. This particular topic and the resources we're using is out of Chapter 9, 9.6. We're going back and picking it up. But we do it after trigonometric ratios because it makes a whole lot more sense in what we're doing and how we're doing it to do it then. There's two concepts. Some of the things that we've talked about this year that you've been held accountable for, extended definitions, are like parallel. Prior to this year, parallel was two lines that never met. After this year, parallel means two lines in the same plane that never meet. And you're now also responsible for the term skew, which are two lines not in the same plane that never touch. Okay, two non-intersecting lines in different planes. Another one is average or mean. Prior to this year, that simply meant mean meant average. Now you know and understand there's two different ways of looking at mean. There's an arithmetic mean, which is the average that you're used to. There's also a geometric mean, which is sort of a multiplicative average that we can find. Both of them have purpose and meaning in measuring central tendencies. But again, another concept in which you now have higher accountability. Same thing with numbers and quantities. Up until this point in time, you've always thought of numbers and things as just being, oh, it's a number. It means this. It's a quantity. It's a magnitude. It's a force, whatever else. Now, and we've talked about direction always being positive. Now what we're going to do is we're going to talk about the concept of scalar versus vector. A scalar being a one-dimensional quantity representing an amount. Okay? One-dimensional quantity representing an amount. A vector being a two-dimensional concept representing both a quantity and a direction. Okay? So how can one thing represent two things? I don't know. We live in a multi-dimensional world, universe. We can have multi-dimensional thought, multi-dimensional concepts, multi-dimensional solutions to challenges. And why can't we have multi-dimensional concepts in numbering schemes? So scalar, a one-dimensional quantity, represents an amount. Vector, two-dimensional concept representing both a quantity and a direction. Concept of scalar: speed, weight, height, altitude, distance. All those are very singular. Speed, 50 miles an hour. Weight, 150 pounds. Height, 6'2". Altitude, 5,000 feet. Distance, it's 20 miles. Whereas a vector, we might represent as 20 miles per hour east. The bicyclist was riding at 20 miles per hour headed east. That's a vector. We not only know how fast they were going, we also know the distance, or we know not the distance, but the direction they were headed. 10 pounds force, 20 degrees from the horizontal. Applying a 10-pound force to something 20 degrees from the horizontal. Not quite definitive completely, but we get the concept that there is a direction to that force. It's not straight down, it's not straight sideways, it's at an angle 20 degrees from horizontal. So we have the concept of an amount and a direction, an amount or a magnitude and a direction. Scalar versus vector. Now let's talk about some other concepts on vectors. Vectors, a vector represents both magnitude and direction. Magnitude by its length and direction by its direction it is on the grid. Standard form of a vector, it's the vector originates at the origin. We pretend it originates at the origin and we have a standard form. Notice that instead of using it as an ordered pair, we have these arrow brackets that we use to denote that it is a vector. Vector 5, 2. It would start at the origin, it would go to the right 5, and it would go up 2. We would draw a line such as that. It would have a run of 5 and a rise of 2. Okay, how would we calculate its magnitude? Well, its magnitude would be the hypotenuse of that, which would be 5 the square root of 5 squared plus 2 squared, which would be the square root of 29. So its magnitude would be the square root of 29. Now, a vector can also be represented anywhere on the coordinate grid, such as vector EF. And notice how we write the term vector EF. It is a vector that starts at point E, goes to point F. And how do we denote that it is a vector? Notice we have a line over it with 1/2 of an arrowhead. That says we have a vector. With, let's say, E is at 1,5, F is at 7,4. Okay? So the vector starts at 1,5. It does not start at the origin, and it goes to 7,4. We can change that to what we call a component form, or so we can determine its magnitude and its direction. It ends at 7, comes from 1. So how far did it run? It ran 6 in the positive direction. It started at 5 and goes to 4. So how far did it rise? It rose a -1. Okay? Notice that we do, how far did it go from its beginning to its end? It went a +6. It went a -1. Okay? This is known as the tail. This is known as the head. Okay? And we'll talk about that a little bit later on. So, from its tail to its head. Okay? And we're going to head that direction. And it would be like this. Okay? Now, what's the difference between component form, this down here, and standard form? As far as its representation, none. Component form, we know, could have taken a vector that could be anywhere on the coordinate grid and represents its direction as if it were placed at the origin. It's like we move that coordinate grid to the beginning point where the tail is, so that we can determine exactly what its run and its rise is. Okay? So there's not a tremendous amount of difference as far as what we're concerned with right now on what standard form is and what component form is. Component form typically is going to come from a vector that is out in the middle of the coordinate grid. And we're going to have to calculate that as if we moved the coordinate grid to the origin is at the tail. Okay? New concept, standard form. Vector originates at the origin. Okay? So it starts at, the tail would be at 0, 0. Its head would be at wherever we have it. Notice how we denote that it is a vector. Also, a vector can be represented anywhere on the coordinate grid, such as a vector. Here's how we say a vector starts at point E, goes to F. And that's how we say it's a vector, with E at this point and F at this point. This will be known as the tail. This will be known as the head. Component form. This is how we do it. This is where we ended. This is where we started. So what was our run? It was a +6. This is where we ended. This is where we started. What was our rise? It was a -1. Okay, so we end up with a vector of 6, -1. The component form is as if it started at the origin. There's one other concept of vectors we need to talk about before we start talking about magnitudes and directions, and that is a resultant vector. Okay, a resultant vector is the ability for us to take two vectors and add them together and get a resultant vector. Okay, it's really pretty simple. Because we're going to take vector AB, which is at 5, 4, and another vector LM, which is 1, 5, and we're going to take a resultant vector. We're going to create this as if it starts at the origin, and that's what vector AB looks like, 5, 4. It heads to there. Then what we're going to do is we're going to start vector LM at the head of AB with the tail there at L, and we're going to extend it up. Then we're going to draw a new vector, AM, that goes from the tail of AB to the head of LM. Okay? And how do we find out what that vector is? Well, vector AM, our new vector, is simply the addition of vector AB plus vector LM. What is vector AB? It's 5, 4. Plus vector LM, 1, 5. We add the corresponding pieces. 5 plus 1 is 6. 4 plus 5 is 9. So vector AM is simply 6, 9. We can therefore calculate its magnitude. We can calculate its direction, so forth and so on. That's the resultant vector. We can continue this on and on and on and on as many times as we wanted to, adding as many vectors as we wanted to, getting a final resulting vector starting from the tail of the first, going to the head of the last one that we added. That's a resultant vector.